Everything that I'm going to be talking about today is based off of this paper cited here at the bottom of my introduction slide here. Before I begin, I'd like to acknowledge collaboration with Shankar, the head of our group, and also funding from the Laboratory for Physical Sciences. So before I begin talking about the actual subject, I'd like to give a brief introduction to myself, kind of like what others have done in their presentations. So, well, I was born and raised in Florida, and I got my bachelor's, master's, and PhD all at Florida State University before I, came here first as a postdoc and then recently as an assistant research scientist. So my main interest right now is in semiconductor-based electron spin qubits with a focus on errors in performing gates. So in characterizing and also correcting said errors. And sometimes I do graphene-related projects. This used to be a much bigger interest, but nowadays it's mostly semiconductor-based spin qubits. So with that, the work that I'm about to present is focusing on single electron spin qubits. So basically you just have a chain of quantum dots, each one with one electron, and the spin up and down is your qubit state. That's your zeros and ones, or your 0 and 1 states. And we're motivated especially by two experiments that have been performed measuring the fidelity of swap gates in these types of systems. So one of them was performed at the University of Rochester by John Nichols' group, and then there's another one performed at Princeton by Jason Petta's group. Now, swap gates are very important to the transfer of qubit states, so that's why we're interested in determining their fidelity and figuring out how to eventually get it up to the 99.9% threshold that you may have heard about for quantum error correction techniques to work. So here's the model that I'm going to be using for all my calculations. So here we're considering a chain of exchange coupled spins. So there's a chain of L electron spins all spaced with a spacing of A. And what we're including here are nearest and next nearest neighbor exchange interactions. And even though it's incredibly tiny, like by many orders of magnitude in any actual experimental system, we're also including a magnetic dipole-dipole interaction. Now, under ideal conditions, all of the nearest neighbor exchange couplings would be identical, and similarly with the next nearest neighbor couplings, but the reason why these are position dependent, so here J is just the position within the chain, but we need to account for the possibility of noise, which will be present in actual systems, so hence the position dependence of the couplings. So in order to perform a swap operation on two of these qubits, it'll always be on nearest neighbor qubits. Let's first consider the case of just two spins with no noise. So and all we have here is just Heisenberg exchange coupling between the two. So if we let the system evolve under this Hamiltonian for a time pi h bar over 4j, then the time evolution operator will just be the swap operation times a global phase factor of e to the minus I pi over 4. It's unmeasurable. So basically, we're performing a swap operation when we do this. Now, if we introduce more spins, then even if you had no noise and it was just nearest neighbor coupling, you will have crosstalk due to the interactions of the two spins that you're trying to do the swap operation on with other spins that you're not doing the operation on. So that will reduce the fidelity, as we will see shortly. So here's the problem that I'm going to be considering, or it's so we're going to be considering two scenarios. And the first scenario is one in which we prepare the leftmost spin of the chain in the down state, and all the rest are going to be up. So what we're going to do is perform a sequence of swap operations to quote unquote move the down spin all the way to the right. So we swap the first two spins, and then so now the second leftmost spin is down and all the others are up. Now we swap the second and third, similar result. Now the third spin is down, and we keep doing this until the rightmost spin is down. And then we go ahead and reverse this sequence. So now we start quote unquote moving the down spin to the left through a similar series of swap operations until it's all the way back on the left again. The second scenario we consider is one in which we prepare the leftmost two spins in a singlet state. So now they're entangled with each other. So what we're going to do is we're going to do a swap operation on the second and third spins, and what that should do is transfer the entanglement of the second spin with the first spin over to the third spin. So now the first and third spins are entangled, in a singlet state. Then we go ahead and transfer the entanglement over to the fourth spin, and so on and so forth until we reach the end of the chains. Now it's the leftmost and the rightmost spins are in a singlet state. And then we go ahead and reverse this sequence of operations as we did before, like similarly to what we did in the other situation, until we get back to just the leftmost two spins being in a singlet state. So what we want to do is find the fidelity of this sequence of operations for chains of lengths 4 and 6. So in other words, a 4-spin chain and a 6-spin chain. And the fidelity is defined by this expression that I show here, where R represents the ideal operation. So this is what you would have if there were no crosstalk, no noise or anything. It does exactly what we intended it to do. In this case, this is just the identity, and U here is the actual operation performed. So with all the crosstalk and noise effects and whatnot. So basically, this is just the probability that after actually performing all these operations, you're going to measure the system to be in the state that it quote unquote should have ended up in if the sequence of operations had worked perfectly. There were no errors, in other words. So our model for noise in this system is quasi-static noise. So mathematically speaking, it looks a lot like disorder. So we're modeling this as a Gaussian distribution of exchange couplings truncated to positive values. And we do that because in the actual experiments, the exchange couplings will never become negative. So here I have, so this just has a standard deviation of sigma j. So that's what I'm going to be calling that the strength of the disorder, and then J naught is the intended value of the exchange coupling. So this is without the effects of noise. So now to implement our swap gates, what we do is basically kind of like what I described earlier, where what we do is we increase the nearest neighbor exchange coupling between the two spins that we want to perform the swap operation on to some larger value that I denote by J swap, and then just hold that value for a time pi h bar over 4j swap. And if we have next nearest neighbor interactions present, then these next nearest neighbor interactions involving the spins being operated on will increase in proportion to the nearest neighbor coupling. So now I present the results of my calculations. So here are the those two situations I described. Leftmost spin down with 4 spins, and then this is with the leftmost 2 spins in the singlet state, again with 4 spins, and then these 2 plots are for 6 spins, same 2 situations. So what I'm plotting here is the infidelity, so just 1 minus the fidelity as a function of J swap. This is all just for nearest neighbor coupling only, so there's no next nearest neighbor coupling. The dipole-dipole interaction is not present, and there's no noise. So already we can see that there's a degradation in fidelity. And for large values of J swap, so starting around 10, we can see that the infidelity is decreasing to arbitrarily small values as we, increase J swap. And the reason why this is happening is just the higher J swap is, the less time it takes to actually perform the swap operation, and thus the less time there is for the crosstalk effects to really do a whole lot to the operation. So that's why we're seeing this decrease. And you might also notice that there's these oscillations for small values of J swap. So I believe the explanation that I thought of, like the sort of hand waving explanation I had, was basically here, it takes, a relatively long time for the swap operation to happen. So what's probably happening is the crosstalk terms, like the oscillations due to them, are you're going through basically more or less a full period of oscillations that would be due to these crosstalk terms, and you get like partial cancellation of their effects. So that's why the fidelity may actually improve if you, for just for small values of J swap, not for the large values. So probably not important for experiments, but just something I wanted to point out. So now let's add in next nearest neighbor coupling, and we're going to assume that it is 1% of the corresponding nearest neighbor coupling. So this is just a sort of reasonable value that we came up with. This isn't from any calculations or anything like that. So now you can see that for large values of J swap, we're no longer going to arbitrarily small infidelities. It's actually, the infidelity is actually saturating, or it appears to be saturating. And the reason why is because, well, you might remember that when we increase the nearest neighbor coupling to perform the swap operation, we're assuming that the next nearest neighbor coupling is also going up in proportion to that, involving the 2 spins being operated on. So there's always significant crosstalk, no matter how high you set J swap. So that's why we're seeing this saturation instead of just going to arbitrarily low values. So now if we turn on, noise and the, dipole-dipole interaction, which I admit isn't going to be changing our results very much, we see that noise is just making things even worse. The infidelity is saturating to larger values, the higher the strength of the noise, as you can see here in all of these situations. Now, you probably noticed these dashed lines. So the red dashed line represents what we would have if our swap operations had 99.9% fidelity. So, as I said, that's the goal that we want to achieve for being able to implement error correcting techniques. The blue dashed line represents the Rochester group's fidelity, and the black dashed line represents the Princeton experiment's fidelity. So as you can see, it's very unlikely that we would ever be able to achieve 99.9% fidelity just by, cranking up J swap to higher values. We're going to have to find a way to, combat crosstalk in order to achieve this, and maybe also reducing the amount of noise in the system. But we could certainly do better than what we have so far. So how much time do I have?
About 5 minutes.
Okay. Okay, so in conclusion, we investigated the fidelity of performing a chain of swap operations on a chain of spins, showing the effects of crosstalk, next nearest neighbor coupling, and quasi-static noise. With only nearest neighbor coupling, infidelity decreases as roughly 1/J swap for large values of J. Introducing next nearest neighbor coupling resulted in a saturation of infidelity at a non-zero value, with noise increasing the value to which it saturates. So, and as I said a few moments ago, 99.9% fidelity is unlikely unless methods for combating the effects of crosstalk are implemented. And so that's everything, and thank you for your attention.
Okay. Thanks, Robert, for the great talk. Is there any question from the audience?
I have a question, Robert.
Yes.
So it looked like all the graphs that you showed, the strength of the crosstalk was just fixed at like, what was it, 1% of J naught?
That's just the next nearest neighbor.
Yeah. So J prime was fixed as like 1% of J naught, right?
Right.
Robert,
you looked at.
You should go back to that graph so that people know what one is talking about.
Okay. Hold on 1 second.
So that Donovan's question makes sense to others also.
Okay.
Yeah. So have you looked at changing J prime and seeing if there's a relationship between J prime and the value at which it saturates?
No, we didn't look at that. We just looked at 1% of the nearest neighbor coupling. I would imagine that would have effects. Like I could see this, for example, improving or worsening the infidelity depending on whether it was stronger or weaker.
Yeah, I'd imagine that there'd be some sort of straightforward relationship, and I was wondering if there's a way to like quantify that, or.
Yeah, I'd imagine that we could. I mean, it's something I could probably do, but it's just I didn't do that like for the paper that this is all based on. There.
Okay.
Yeah, I think this is a very good idea. This first calculation was really motivated by the question, can they really reach 99.9%? But I agree with Donovan, we should ask some of those deeper questions now.
Okay.
So I have a question.
Yes.
Can you, so you said we basically there's no chance of 99.9% unless we actually mitigate crosstalk. Can you speculate whether that's something that can be dealt with, or like, is that something that has to be dealt with at a hardware level? Is it something that like, you could change some sort of pulse sequences and start doing the correction with the hardware that's currently available?
Yeah, I think it is probably possible to do that with cleverly designed pulse sequences. In fact, you could probably, for example, adapt this technique that was developed here at Maryland for combating errors in singlet triplet qubits. So it's basically just 2 electron spins, and we're using the singlet and triplet states as our 0 and 1 states. Yeah, I could imagine that. So this technique was referred to as a SUP code. I can't quite remember what that stood for. It's an acronym, but yeah, I think it could be dealt with at the software level, definitely. I was kind of trying to allude to that, in fact.
Okay, thank you.
Hey, Robert,
Yes.
I'm just curious about experimentally how they actually do this swap operation.
I don't remember exactly how that worked. I'm tempted to say that the Princeton group may have actually like used an oscillatory like pulse. So here I did it a little bit differently. I did it differently. I just fixed the exchange coupling at some value. I don't remember how the Rochester group did it. I'd have to look it up again.
Well, the basic principle is straightforward. What you basically do, you have this line of spins. Each spin is really a quantum dot. So you have 4 quantum dots. They're like, maybe 100 electrodes controlling this quantum dot. So they can put electrons at will in this quantum dot and take them out, and each of them is a spin. And then they have a technique of measuring spin. So they do various pulses, which in the simplest case, they know the spin can be rotated. So they rotate the spins and then they measure spins. This measurement of spin can be done very, very fast in semiconductors. Basically, you can do spin selective measurements very, very fast by using something that's called Pauli blockade. It's the same technique as in single electron transistor, that if you want to put an electron in a place where there is already an electron, you have a Coulomb blockade classically and Hubbard U quantum mechanically. And since in the end, all you're measuring is charge, you're really not measuring spin. You're just using the fact that the charge that you are measuring is spin polarized. It can be done very fast. So that's all they're doing in principle. Does that answer your question?
Yes, thank you.
That's the reason semiconductor spin qubits will remain around for a very long time. You can do the operations very fast, and you can do the measurements very fast. So it's like orders of magnitude faster than any of the other quantum computing schemes around in practice, whether it's superconductor or ion trap or any of them. The problem is that these things are tiny, right? They are like we are talking, 10 to 50 nanometers. So you can scale them up easily, but tiny means that fabrication on those things are much, much more difficult and much, much more error prone. So, the advantage is also a disadvantage.
And of course, I think also like noise, I think is a bigger problem, if I'm not mistaken too, or at least I know that like, fidelities aren't as good as on, the semiconductor and ion trap systems.
Yeah, they are all connected because they're so small. They're easily perturbed, you're right. But this same noise, this charge noise, affects the other ones also. And my view is that whether you have 4 qubits or 40 qubits may make a difference in terms of your ability to write papers in glossy magazines, but it makes no difference whatsoever in your ability to create a quantum computer. Both are equally useless, meaning, if in the end you need 10 billion qubits at 99.9% fidelity, and somebody has 4 qubits with 99% fidelity or 98% fidelity, and somebody else has 40 qubits with 99% fidelity, as far as quantum computer goes, there is, it's not clear that one has an advantage. So eventually, how you fight this noise is an open question. It's not known. So, and it's a problem for all the qubits at this stage.
Thank you.
And I also have a question. Here's Jabin. So I might miss this point, but how experimentally tune the J swap while fixing the ratio between J prime and J? It is possible to do that in experiment?
Well, I don't know if that's exactly how it's working. Like that's just an assumption that I'd made in my calculation. It's okay. I think it's just like a reasonable sounding assumption. Like, you make the interaction, between two spins, large, or like the direct, nearest neighbor interaction, then that's probably going to have some effect on the next nearest neighbor interactions as well. Like just due to the fact that, with exchange, that involves like virtual, tunneling. So if, you make that easier, you're going to get larger.
Okay.
Yeah, so the answer, again, exactly how it's done is quite technical in the experiment. But the basic principle, again, is very elegant and very simple. As you know, in real life, there is no spin. You only have electrons or protons or neutrons. There is no object called spin. Spin comes always in the particle, right? So all the spin models that people use are fundamentally fermion models, right? So what is happening here is that what you have is real electron, and those electrons have spins, and their wave functions overlap, and this overlap leads to Heisenberg coupling. Okay.
Okay.
Now they can, again, in semiconductor, this overlap between two neighboring electrons can be controlled to an incredible precision. And the reason it can be done is literally they use gates to do wave function engineering. So they can, make these wave functions long, fat, or very short by cutting off using gates very fast. So that's how they control these things, and they have very good control, but not perfect control. I don't know if this answers your question, but yeah, they can.
Sure. Yeah. That's answered my question.
Using gates, and that's why this control is very fast. Again, sub-nanosecond.
Thanks for your explanation.
Hi, Robert. This is Heini.
Yes.
I just wonder, why do you compare L equals 4 and 6? Because to me, 4 is not much different from 6.
Well, this is just because this is about as large a system as they have out there for like an actual experiment. So we don't have very large chains of spins. I mean, I know that there are some people who've claimed like 9 qubits, but it's in a slightly different architecture than what I'm considering here. Like it's something like, I think it was a phosphorus donor type qubits. But yeah, as far as these quantum dot based systems, that none of the experimental systems are particularly large. Like I think 4 spins is maybe about as large as they've built. So 6 is just a little bit beyond 4, and also and also like the scales are a bit different on my plots. Like visually they may not look very different from one another, but yeah, just notice the scales here. Like the infidelities for the 4 spin case are quite a bit lower. Like you see, the scale is going a bit lower than on the 6 spin case. So there actually is quite a bit of difference between the two.
And I also have another question: is why there is a dip in a single qubit around like 2 or 3 for both L equals 4 and 6?
Oh, you mean these oscillations here?
Yeah.
So as I was saying before, I don't really have a rigorous explanation for what's going on here, but my sort of hand waving explanation is just simply that the at this at these small values of J swap, there's actually probably enough time for like oscillations coming from the crosstalk terms to go through like more or less a full period. So you're seeing basically a partial cancellation of the crosstalk effect. So you're seeing these. So that's probably what's causing these dips. As I said, this is not like a rigorous explanation.
I'm pretty sure that's what is going on. For very slow J, some at very low J, they are all equivalently important. And you can easily check it by suppressing the crosstalk. I think if you put the crosstalk term to be 0, this will go away.
Yeah.
Okay, maybe we can continue the discussion afterwards. Maybe we should move on to next talk.
Okay, I'll go ahead and stop.
Thank you,
Share
Robert.
there. All right, you're welcome.
Okay, so next talk will be given by Professor Victor Yakovenko. He has done many amazing, has made many amazing contributions to almost all fields of condensed matter physics, including like unconventional superconductors, metal insulator transitions, semifermions, 2D electron gases, quantum Hall effects. He also applied the statistical physics to economics and finance, and really deepen our understanding around of our world. So today he's going to tell us about how to measure Hall conductivity in a superconductor. So let's welcome Professor Victor Yakovenko.
Okay, thank you. Okay, so this is basically work was done with my PhD student Lance Boyer, who graduated last year, 2019. So he didn't have a chance to present this work at the CMTC Symposium. So I'm kind of presenting this work for him. And also, I mean, upon graduation, he got a job at Applied Physics Laboratory in Maryland. So this talk has a little bit of flavor of applied physics, but in any case, it is a proposal for an experiment, whatever it means. Yeah, so basically it's a proposal how to measure spontaneous Hall conductivity in a superconductor. And I will start with some introduction. I'll have like 3 or 4, 4 or 5 slides introduction, which I would like to get kind of through quickly. And then the main part will be the actual proposal, but I need to have some introduction to get there. First, I'll briefly discuss time reversal symmetry breaking in superconductors, and that is a subject I have been working on, in the recent years. And so this work is one of a sequence of line of work about time reversal breaking superconductors, and I will mention some other work in the process. So I'll briefly discuss polar Kerr effect versus DC Hall effect, and then basically switch to Corbina geometry, which is basically the main subject of the talk. Okay, so let me start with the introduction. First of all, one slide on superconductors that break time reversal symmetry. Well, there are several materials, it is not an exhaustive list, some number of them, that when these materials undergo superconducting transition, that superconducting state breaks time reversal symmetry. So the point is, these are not, magnetic superconductor, meaning there are some materials that have magnetism already, and then they become superconducting. But here, they are not magnetic before superconduction transition. They then break time reversal by superconductivity. And so the first material was widely discussed was strontium ruthenium 04. It was proposed to have like px plus ipy pairing, which basically means, well, in a nutshell, I don't want to go into actual realistic details, but if you have some Fermi surface and you have superconducting pairing, and superconducting pairing has a phase, which is function of momentum. So if this phase has a winding, like say 2 pi winding around the Fermi surface, that can be clockwise or counterclockwise. So that breaks time reversal symmetry. And physically, it means basically Cooper pairing with angular momentum, non-zero angular momentum. So in a 2-dimensional case, angular momentum can be clockwise or counterclockwise. And so each state, of course, has angular momentum and breaks time reversal symmetry. So that's basically a rough idea. I mean, in reality, it is a lot more complicated than that, but that's not the subject of the talk. So let me take it less like, just a flavor of the idea. The real question is, suppose we have this kind of superconduction pairing that breaks time reversal symmetry. How can we possibly detect it experimentally? That is a very challenging question because transition temperature is like usually few Kelvin, so it's really low temperature, and effect is very weak. So essentially, this evidence, the experimental evidence, came from a number of papers by the group of Kapitulnik, and this was actually optical measurement. So this was okay. So that in the presence of, say, magnetic field, suppose we have magnetic field extrinsic or maybe intrinsic because system spontaneously breaks time reversal. There are 2 kinds of optical effects that we can discuss. One is Faraday effect. If you send linearly polarized light through the sample, the polarization plane rotates by some angle due to the presence of magnetic field. So that can be taken as some signature. However, it also can rotate if system breaks time. It's just inversion symmetry, like sugar, for example. Molecules break inversion, and it also produces rotation of polarization. So in that sense, Faraday effect is not conclusive. But then there is similar effect for reflection. Faraday is for transmission. That's called polar Kerr effect. When they send beam of light, linearly polarized, and it reflects. And if system breaks time reversal symmetry, then the polarization plane would be generally rotated clockwise or counterclockwise because of the time reversal symmetry breaking. It's important that a so-called polar Kerr effect means you have normal incidence and normal reflection. So in this case, there is a general theorem, basically Onzeger's reciprocity principle, which says that if you do normal incidence and normal reflection, polarization plane can rotate only if system breaks time reversal. So from that perspective, it can be taken as conclusive evidence of time reversal breaking. And that was implemented by the group of Kapitulnik. The problem is the effect is very, very small. So it is in nanoradians. So you cannot just measure it like, by angle. So they invented, they came up with a very complicated scheme. I'll show next slide. It's interferometry. So it's another kind of interferometer that can measure, has capability of measuring this kind of accuracy of nanoradians. So there are, and this is a very challenging experiment, and there are some kind of issues with that. A signal is very weak, extremely weak. Also, they use pretty high frequency of the order of electron volt because they use telecommunication cables, which is frequencies way above any scale for superconductivity, which also doesn't seem to be optimal. You would probably want to have lower frequency, which is kind of commensurate with the scale of superconduction gap, but that's not the case. They measured very high optical frequency and signal is very weak. And the main problem is that basically, I think this is kind of the main problem. So right now in the world, there are only two operators, that can do this experiment. The original one in Stanford, which was built by Zhang, who was a student of Kapitulnik at that time. And then Zhang, himself now is a professor at Irvine, and he built second copy of it. And so, all this evidence comes only from this basically same group, if you like, of people. And there's no, well, in the first approximation, there's no alternative confirmation. So let me just show the apparatus very, very quickly. They call it Sagnac interferometer. I don't want to go into detail, but basically they have an optical fiber. They send the signal. The signal reflects from the sample and goes to the same fiber. Before they hit sample, there is quarter wave plate that transform linear polarization to circular polarization and vice versa. So long story short, they have one beam of light that goes in one polarization called, say, horizontal, and reflects in another one which is called vertical. So this optical fiber has two modes, vertical and horizontal. So you send basically signal in one mode, it comes back in a different mode. At the same time, you send reverse signal in another mode and comes back in the original mode. So basically you have two beams coming back and forth, and these two beams are time reversal of each other. And then you measure interference between them. And if there is non-zero phase of interference, there's non-zero phase, that means this sample, reflection from the sample, breaks time reversal symmetry. So that's basically the idea. In reality, it's a lot more complicated than that, but that's how it works. So, as I said, there is only two copies of this apparatus in the world. And this is the result that they obtained using this apparatus. This is my more or less last introductory slide. They first measured this material, and then various other materials, uranium, platinum 3, whatever. There are half a dozen materials by now. This is not an exhaustive list. So the typical observation is that this is what's called Kerr angle, the rotation of polarization, of interference between these two beams, which is basically zero at higher temperature, and at superconducting transition temperature, a non-zero signal appears. And of course, because it is spontaneous symmetry breaking, it can have positive sign or negative sign. In other words, these Cooper pairs can be clockwise or counterclockwise rotation, and so they can see the positive signal or negative signal, and they can control positive or negative, if they want to. They can do measurements of zero magnetic field, in which case the spontaneous symmetry breaking, or they can apply some what's called training, training magnetic field, some very weak magnetic field, so it produces some small asymmetry and makes preferable for a system to go this way as opposed to this way. Then they turn off this field and do measurements on warm up, but there's no magnetic field present. And so basically they can control at will positive or negative signal, which also proves that the absorbed signal does couple to external magnetic field. In that sense, it's sort of a proof. It sort of indicates it breaks time reversal symmetry. It couples to magnetic field by symmetry. So anyway, so far, and the signal is in the scale of nanoradians, as I mentioned. So that's basically the end of introduction. And now I'm getting closer to the actual main part of my talk. So so far, these measurements that I discussed were done at very, very high frequency. Okay, and the question is, can we do measurements at lower frequency? Let's say ideally at 0 frequency. So this graph here, and this other paper, that's my earlier paper in collaboration with other people. So what we did in this paper, we studied some toy model of superconduction pairing on hexagonal lattice with time reversal symmetry breaking. And it's just a toy model, it's a 2-dimensional, so we can calculate everything. So we calculated everything. So in particular, we calculated AC hole conductivity. So you simply calculate linear response, Feynman diagram for hole of diagonal conductivity response, and we calculate as a function of frequency. Okay. So, and we get a curve. So the red curve is the real part of hole conductivity, and the blue curve is the imaginary part. So, and Kapitulnik's experiment is somewhere here at a very, very, very high frequency where signal is very, very, very weak. But the same calculation, the same theoretical calculation tells us that there should be a non-zero DC hole conductivity. So not surprisingly, time reversal symmetry is broken, some hole conductivity is permitted. So generally speaking, we expect this time reversal breaking superconductors to have a spontaneous non-zero DC hole conductivity. Okay, that's permitted by symmetry, and it is calculations, at least in toy model give some value for it. So the question now is, so we denote it sigma h, this spontaneous hole conductivity. The question is, can we actually measure it experimentally, preferably at GC, but maybe it's not DC, maybe at low frequency, at very low frequency. And that is a problem. There is a difficulty of doing this in a superconductor. And the problem is the following, that the usual way to measure hole conductivity, one typical is called hole bar. So essentially you take your sample, how experimentalists measure hole conductivity? They pass current through the sample and they measure transverse voltage. And if there is non-zero transverse voltage, then system has Hall effect, and this is Hall resistance. Okay. The problem with superconductor is there is no voltage. You can surely pass current, not a problem, but there will be zero voltage, because in superconductor the current is a sum of supercurrent. Well, generally speaking, it's the sum of supercurrent and whatever else. For example, Hall current. But the problem with supercurrent will shunt out everything. If you send current, it will be carried by supercurrent, and there will be zero electric field. And in the absence of electric field, Hall current will be also zero. So the problem is we have a situation where the coefficient it may be non-zero, but the Hall current is zero because we have difficulty putting electric field inside superconductors, because they basically screen, it's very difficult to put electric field inside superconductor. You cannot just connect a battery to a superconductor. So that's a problem. And so basically our proposal to kind of get around this problem is to use different geometry, specifically Carbino geometry, because there is another geometry for measured Hall effect proposed apparently like more than a century ago by Carbino, instead of Hall bar. And by the way, I also want to mention in the case of Hall bar, the usual, people often discuss in terms of H currents. They say if there is voltage, then there will be, H currents, and imbalance of H currents, it gives Hall current. So, Hall is often discussed in terms of H states, but it can be equally well discussed in terms of Carbino geometry. So let me just quickly remind how it works for Hall insulator as a warm-up. And in fact, this experiment has been done, this experiments have been done. So let's take a Hall insulator as a warm-up, not a superconductor. So Hall diagonal conductivity is zero. Of course, in superconductor, it's the opposite, because now we're talking about insulator, and there is non-zero Hall conductivity. So how this Carbino method works? You apply magnetic field perpendicular to this disk, and magnetic field oscillates in time. So because magnetic field oscillates in time, it induces, by Faraday's law, it induces circular electric field. So you induce circular electric field in this system. And then, of course, once you have circular electric field, if there is Hall coefficient, there will be radial Hall current. So importantly, in this case, the Hall current is radial. Okay, so it does not go around the edge. To the contrary, it goes from one edge through the bulk to another edge. So that's this Hall current, radial Hall current induced by circular electric field, which is induced by oscillation magnetic field. And so basically then this radial current results in accumulation of charge. So there is charge accumulation on the boundaries of the inner and outer boundary of the sample. And that produces a radial electric field because you have charge accumulation. It produces radial electric field, kind of electrostatic radial field, which produces voltage. And that's basically what you measure. So what experiment measures voltage between the inner outer part of the sample in response to oscillation magnetic field. And that's basically the formula. And in this way, you can extract Hall conductivity. So that's kind of, in principle, well-known method. Now, what we want to do, now I'm getting to actual subject of the talk. We want to basically adapt this method to superconductors. So now we use basically the same kind of geometry, but now our material is superconductor. I should emphasize that the actual calculations done in the case when we have a superconducting cylinder. So, I mean, not that it's realistic for this experiment, but it's easier to do calculations if everything is like long along z-axis. So this picture is drawn as a flat cylinder, but what we have in mind actually a kind of a long cylinder. Anyway, let's take a superconducting cylinder, put in magnetic field, oscillation magnetic field. And then the problem is, unlike in the previous example, so this magnetic field, oscillation field, will produce circular electric field by Faraday's law. It's kind of good news. Okay, we get circular electric field in a superconductor. But the problem is that the circular electric field in a superconductor will induce supercurrent, will induce accelerating circular supercurrent. And this, of course, circular supercurrent will induce the opposite magnetic flux. So now we have circular supercurrents which induce the opposite magnetic flux, which of course will screen magnetic field. So this is well-known Meissner effect. So as a result, magnetic field will be screened except for the London penetration depths. So bottom line is magnetic and electric field, magnetic and Faraday electric field will not actually penetrate deeply into the bulk. It will only penetrate within Meissner lengths. Okay. And that's kind of bad news, but maybe not so bad. Bad news is that it does not penetrate in the bulk. That's not so good. But not so bad news is it still penetrates within London lengths. And so the idea is to use penetrating magnetic and electric field within London lengths to measure Hall conductivity. So in a nutshell, there will be still electric field present within London lengths, and this circular electric field will induce radial Hall current. And this radial Hall current then can produce charge accumulation, which can be measured. Okay, so that's shown more in detail in the next slide. So the next slide, I show kind of side view. Imagine the cylinder, and we look from this side. We look kind of from the side. So that will be the picture. So this is, again, this is a magnetic field. This is my cylinder extending in this direction, and we take a side view. So this is radial coordinate. Okay, so let's see what happens. So once we apply the oscillation magnetic field, it produces circular electric field, and that produces radial Hall current. Okay, so we get radial Hall current. This radial Hall current will result in charge accumulation on the inner and outer part of this, let's say on the outer wall of the sample. But this charge accumulation will, of course, produce electrostatic electric field, radial electric field. And once you have radial electric field, it will produce radial supercurrent. So we always have to deal here with supercurrent and Hall current. So we'll get radial supercurrent, and that radial supercurrent will, related to the accumulated charge. And so, long story short, we will have some equation of motion for the charge. So accumulation of charge on the boundary will have two contributions. One from Hall current, which is in this radial direction, another one from supercurrent, which is induced by charge itself. If you collect all these equations, substituting all this here, then we get a second order differential equation, which is nothing but plasma frequency oscillations. So if you don't have any Hall conductivity, forget about any Hall currents. So then if you simply produce some charge here, the charge which oscillate with plasma frequency, because, well, a superconductor is a very good metal, so it has plasma oscillations. So if there is excessive charge here, we just oscillate with plasma frequency. So that is the kind of homogeneous equation. But now the important part is, if we have non-zero Hall conductivity, so we have Hall current, the Hall current appears on the right-hand side of this equation. So the Hall current is like a source or the driver in this kind of plasma oscillator. And if you substitute the formula for this, and the source here is proportional time derivative of the Hall current, if you substitute the formula, basically we have a right-hand side source, which involves second derivative of magnetic field. So the bottom line is, if we have a non-zero Hall conductivity and we have oscillating magnetic field in this direction, it will be a drive, like force. It will cause forced charge oscillations of plasma frequency. So basically, this, of course, a differential equation is easy to solve in Fourier domain, and this is basically the answer. So the charge, the oscillating charge on the boundaries of the sample, is proportional to the oscillating magnetic field, like axial magnetic field, with coefficient which has Hall conductivity and a bunch of coefficients like plasma frequency, London length, etc. And of course, this charge accumulation on the outer and inner walls, it produces radial electric field and radial voltage. So if you substitute the stuff, you'll find that there is radial voltage between inner and outer part of the sample. And this radial voltage is proportional to applied magnetic field, has Hall coefficient. And also, I should emphasize, it has a frequency omega squared. So it needs a frequency omega squared because you need time derivative of magnetic field to produce, Faraday's electric field. And another time derivative comes because, it's time derivative of Hall current, which is the source of this plasma oscillations. So basically, at the end, the measured effect, the measured signal is proportional to square of frequency of the oscillating field. So in that sense, it's strictly speaking not a DC measurement. You have to have non-zero frequency, but this frequency can be like relatively low. I mean, it will be like radio frequency, maybe microwave frequency, but not the optical frequency. It's still maybe quasi-static frequency. In some sense, this formula is sort of the almost like final result of the paper. So we predict voltage. It can be radial voltage induced by axial magnetic field due to Hall conductivity. But I need to say a few more things. One thing, I have a couple slides left. One thing I wanted to mention is the following. That's kind of frequently asked question. You see, since we apply already magnetic field, you may ask, well, you apply magnetic fields. Once you apply magnetic field, there will be Hall conductivity anyway in any material, right? So wouldn't these two things get, can we distinguish a Hall effect just induced by magnetic field with intrinsic Hall effect? And the answer is yes. Because, okay, so, in any material, there is Hall conductivity induced by applied magnetic field. Let's call this coefficient SH, as opposed to sigma h. So SH is a coefficient of proportionality between Hall conductivity and applied magnetic field. And so what we see here is that, well, if our magnetic field oscillates, then our Hall conductivity will also oscillate. And then we go through the same procedure that we did before. We get Hall current and everything. But you see, we have Hall current related to time derivative of magnetic field. But the difference is that the Hall conductivity itself here is oscillating. So long story short is, for this time-dependent Hall current, this term oscillates with frequency omega, and Hall conductivity also oscillates with frequency omega. As a result, you get a signal at frequency 2 omega. So in other words, if you take a material which does not break time reversal symmetry by itself, you would have the same effect as I discussed before, but it will be, we have radial current, radial charge, but it will oscillate at frequency 2 omega. It will be second harmonic generation. Whereas if you have spontaneous Hall conductivity, the response will be at the same frequency. So by measuring response at frequency omega and 2 omega, you can distinguish, intrinsic Hall effect and just conventional induced Hall effect. And finally, some numbers, 2 slides and I'll finish. So numbers, now we need to plug some numbers, do some estimates. Well, first of all, the question is, what is the order of magnitude of Hall conductivity in a superconductor? And again, we did this calculation in the previous paper. And the answer is the following. Well, first of all, we can use E²/h, but it's a layered material, has many layers, so we need 3-dimensional Hall conductivity, so we need to divide by distance between layers. And by the way, natural units for the 3-dimensional Hall conductivity is actually frequency, because if you see here, it's electric E² divided by distance, that's Coulomb energy, divided by Planck constant is frequency. But there is also a prefactor, delta²/EF. So Hall conductivity in superconductor is actually reduced by a factor of delta², because you see, you need superconductivity to have Hall effect. If there's no delta, Hall effect is 0, because time reversal breaks for superconductivity. So it's proportional to delta and proportional to delta² because it has to be bilinear in delta, for gauge invariance and all that. And so bottom line, you have a pretty small prefactor here. So then, so next story is that this is, anyway, so that reduces the magnitude of effect. For comparison, I do this for the 2-dimensional Hall effect, where in fact, Cardina measurements have actually been done experimentally for 2-dimensional quantum Hall insulator. So anyway, if I go through the numbers, I don't want to bore you with this. the conclusion is that the induced voltage, the estimate of voltage for some kind of quasi-realistic parameters is like 2 nanovolts for superconductor, whereas for Hall insulators was 10 millivolts. So it's surely much easier to measure 10 millivolts, and that was actually measured experimentally. But for superconductor, unfortunately, it would be like, several orders magnitude smaller, 2 nanovolts. So it's a very challenging experiment. How would you measure induced voltage of like a few nanovolts? And finally, the proposal is to use coaxial cable, contactless measurements using coaxial cable. So this is basically the idea. This is your sample. This is superconductor, the cylinder, superconducting cylinder with a hole inside, then there is magnetic field, applied vertically and oscillating. And this oscillation magnetic field will induce radial voltage. So radial voltage between two sides. And how are we going to pick this voltage? The idea is we have radial electric field E, okay? And then what we do, we connect the system to a coaxial cable. So this is the coaxial cable. This is a central, central rod, and this is the outer part. And so the idea is in coaxial cable, I teach electrodynamics, upper level electrodynamics undergraduate course. You have a coaxial cable, and if you have radial electric field, then it induces propagating electromagnetic wave. So this is contactless measurement. There's actually no electric contact. This thick line is supposed to represent insulating contacts. So basically, once you have oscillation electric field, it will induce electromagnetic wave propagating on the cable, and then you pick it up, amplify, etc., and do the measurement. And so we just compared with the signals like 10 to the minus 20 watts. So the power is extremely small, but quantum limit is like 3 orders of magnitude smaller. So hopefully it can be done. I'm not sure whether it's a very big challenge. So there is a chance it could be done. And so that's basically brings me to conclusion. So we propose a low frequency Hall effect measurements as an alternative to high frequency polar Kerr effect. Unfortunately, this experiment looks to be as challenging as this experiment, but for different reasons. But at least it could give us alternative confirmation of time reversal breaking. So basically, what we see is that axial. So if you have non-zero Hall conductivity, then axial magnetic field produces radial charge oscillations in a superconducting cylinder, Carbina geometry cylinder, and this radial signal can be, and terahertz frequency maybe, can be picked up by coaxial cable and measured. So that's pretty much it. Thank you very much for the attention, and I'm done, and I can ask questions if there are any.
Okay, thank you very much for the interesting talk. Is there any question from the audience?
Can I ask one question?
Okay.
Yeah.
Okay. So just one quick question. I see you separated the Hall current from the supercurrent. Does that mean the Hall current is given by electrons that do not form Cooper pairs?
Okay. Okay. So let me go back to. Let me try to go. Okay, just a sec. Let me go. Okay, no. Okay, let me go. So this, I guess, it's about this slide where we have Hall current and supercurrent, right? That slide, right? You're asking about this? Yeah. Okay. Yeah. So that's very important slide and very important kind of message and distinction. So generally speaking, okay, I'm all there. Yes, here it is. So generally speaking, you see. So generally speaking, there are contributions to current, right? I mean, so the current, electric current, right, is a sum of contributions. So for example, if you have like, gradient of superconducting phase or things like that, that produces supercurrent due to superfluidity and all that, right? If you have gradient of superconducting phase, that's called supercurrent. But also, you see, if somehow the material happened to have a non-zero electric field, if it managed to penetrate somehow, then if this material breaks time reversal symmetry spontaneously, then generally it is permitted by symmetry to have a non-zero Hall coefficient. So that means once you have electric field, you would have perpendicular current. And this is just Hall current, linear response induced by applied electric field. That gives another contribution. So in other words, there is a collective supercurrent, and there is like, linear response transport current. Okay, so generally speaking, superconductors, generally speaking, they have conductivity tensor. For example, there may be some quasi-particle dissipation which will have, have like Drude-like conductivity. Well, anyway, some conductivity. So point line is, generally speaking, whole current is a sum of two contributions. The only problem is that usually, when experimental measurements, the supercurrent dominates, and you cannot experimentally pick up signature of this other contribution, because for this you need the electric field, and usually, very difficult to apply electric field. Yeah, but if you manage to apply electric field, then there will be additional contribution, and very importantly, it's a transverse contribution. So and that's basically that's why we propose this geometry, yeah, to pick up transverse whole current. Yeah, I'm not sure if I answered your question.
Okay, just one follow-up question. Does that mean that the whole current is not related to the Cooper pair phase?
That is a very good question. That is a very good question. I mean, okay, so it is true. Okay, so supercurrent is directly proportional to the gradient of superconducting phase. That's your standard, supercurrent. Okay.
Yes.
But then and what we did in this paper, we use like kind of BCS style, theory of superconductivity, except that your superconduction pairing has, non-zero angular momentum, so it breaks time reversal symmetry. So there is phase winding, etc. And we take this model of superconductor. It's actually toy model, intentionally simplistic, And for this model, we simply calculate linear response. Okay, maybe I should draw it. We calculate the diagram, AX, AY. You just calculate, the linear response diagram. And we find that this off-diagonal AX, AY diagram is non-zero. I mean, first of all, function of frequency. We do this at a frequency, right? It's AC response in general. And we find this response is non-zero. So this transverse response is non-zero. And it is permitted by symmetry because of a superconduction order parameter breaks time reversal. Of course, above superconduction transition, the order parameter is zero. so this diagram would be zero. But once you go into superconduction state and calculate the diagram, you find a non-zero whole coefficient. Okay. But that's coefficient of proportionality between electric field and current. So it's not, it comes from superconductivity, but it's not coming from gradients of superconducting phase.
I see.
It comes from kind of winding of the order parameter in the around the Fermi surface, if you like.
I see.
Yeah, that's what it is. Yeah, so that's basically the thing.
Okay, thank you.
Victor, I have a quick question. When you show this cylinder shape and the charge accumulation for the superconductor, can you go to that slide?
Yeah.
It's just a clarification question because you show like a one charge like accumulate on one side. I'm just curious, where is the opposite charge?
I see. That's a very good question. So okay, very good point. So basically, I demonstrate on the next slide that there is charge accumulation on this edge, right? Yes. But of course, total charge must be zero. So the question, where is the rest of the charge, right? And the thing is, we do not expect charge on this edge, on the inner edge, because too far, everything is screened. Nothing happening there, everything is screened. So what happens is there will be actually bulk charge here. So there will be like positive charge on the outer edge, and the negative charge, it will be actually distributed within the Meissner lengths. Okay. So in other words, you have some kind of charge polarization, separation of charges happening within Meissner lengths. So one charge accumulates at the boundary, that's well kind of sharply defined variable, and the counterpart of it, the negative counterpart, it's actually distributed with some charge density within Meissner lengths. And then here, nothing really happens outside Meissner lengths. So basically, we have to solve coupled equations. It's basically solving, Maxwell's equations, for electric magnetic field with constituent relations, currents, which include supercurrent and whole current contribution. So once we solve all these coupled, partial differential equations, we find, charge distribution and everything. And so for that reason, the electric field is also concentrated here. So electric field, maybe I should write like electric field. Maybe I should like electric field, like positive charge and negative here. It is all confined within Meissner lengths, and then there is nothing outside. Yeah, but charge is conserved, so don't worry. I mean, there is no violation of fundamental principles.
Sure. Thank you.
Okay, so maybe we should move on to the next talk if there's no more questions.
Let me stop sharing. Okay.
So The next talk will be given by Ruixing Zhang, who is a JQI fellow in CMT and postdoc at CMTC. He's recently mostly focused on studying topological phases, like higher order topological phases, higher order topological Dirac superconductor as Dirac semimetals, and also more recently, he started to think about Floquet topological phases. And I think today he's going to tell us about his recent work on higher order Floquet topological phases. So let's welcome Ruixing. But now I see the presenter's view. And I think you are muted.
Can you hear me now?
Yes.
Yeah.
Okay, let me try with the slideshow again. Now it's in the prisoner mode.
Now I see the PowerPoint.
I think it's okay now.
It's not in the full screen mode. It's
Is it in the full screen mode?
hold on.
No.
Hold on.
Let me see.
It's a little bit slow here.
How about?
Sorry. Oh. Okay.
I guess I somehow get disconnected. Is that right?
Right.
Yeah, try again.
Okay, so I don't know what happened. Okay, so let me start sharing. How about now? It is good?
Just hold on. We are still, yeah, now it's good.
Okay, cool. Yeah, I don't know how this happens because in my previous Zoom talk, we don't have this issue. Okay, so anyway, so hi everyone. So I'm Ruixing. I'm a postdoc at CMTC, and this is basically my where I came from. I came from a small city in northeastern part of China. It's called Dongying, and it's located at the delta of the second longest river in China, which is the Yellow River. And if you're familiar with the geography of China, then this is my small city is actually a 4-hour drive from Beijing. I call it small city, but it still has a population of about 2 million. But in China, this is a pretty small city. So I graduated from the University of Science and Technology of China in 2012. And after that, I moved to Penn State to continue my PhD study, where I work under in the group of Professor Josh Mills' group, and mainly focus on the topological physics of matter, especially topology insulators. And in 2018, that's when I joined CMTC. Okay, so okay, good. So let me just briefly introduce my interest in my undergrad. I'm quite ambitious, and I'm generally interested in what Einstein feels to accomplish. But after and plus some hobbies like playing soccer, singing, writing, and enjoying food. But in my PhD study, after being tortured by the reality of life, I'm now generally interested in anything that is publishable. I have a very diverse research interest, mainly in topological physics, and also enjoying where to find free pizza and cooking authentic Chinese food. So here, I mean, I highlight authentic because.
Ruixing, I have a question. What is authentic Chinese food?
Yeah, that's what I'm trying to elaborate. So authentic Chinese food means something that you cannot get from Panda Express, but probably from Rockville.
Okay. So I have only eaten authentic Chinese food all my life then. Okay.
Okay, great.
There's so many different kinds of Chinese food, right? I mean,
yes.
So many different kinds, right? Kinds and types, right? I mean.
Yes. But those restaurants in Rockville, they are pretty much authentic.
Okay, good.
as a postdoc, I'm recently interested in exploring this very new field called higher order topology, and especially how to use higher order topology to propose new Mariana platforms. Recently, I became interested in Floquet systems, and I'm looking forward to do something slightly more correlated in the near future. For example, these two-state ballet graphene. But at the same point, this year, I'm developing a new interest, which is about losing weight. So I think I managed to find an adiabatic path that connect that actually in the past 6 months that I lost about 30, 40 pounds from XAR to medium. Okay. All right, so this is a very brief review of what I've done at CMTC. So I have done a lot of topics on higher order topology in collaboration with Zhang and also Jay. So in different material platforms. If you're interested in any of these, we can talk later. And also I have I have been collaborating with Fengcheng and Zhang on this framework of describing band structures, band series of 3D twisted structure. And we found that if you like twist a graphite in this way, and you actually can achieve something called a magic angle wire fermion in 3D. And this is a recent work that I'm collaborating with Zhicheng, who I will introduce later, where we propose to use Floquet engineering to generate fragile topological states. Okay, so back to my main topic today. I want to tell you our recent story on this something called anomalous Floquet higher topology, and this work was just posted 4 days ago on arXiv, and here is a reference. So back to my collaborator, Zhicheng. I think he's now in the audience. He's a postdoc at GQI and working with Alexei and Mohammed. Okay, so let me first, introduce some very basics about Floquet theory. I will move. So I think everyone here should know some basics here, but I just want to point out that for this Floquet system, it is crucially distinct from the static system because the so-called Floquet bands are actually periodic in these quasi-energies, and also. The time evolution operator by itself is not time periodic, right? So it is really convenient to define something called a return map operator, which is simply a periodized time evolution operator. And another concept that I want to introduce, probably this is not quite familiar in the community, is something called a phase band. And this is simply the eigenspectrum of the time evolution operator, as well as for the return map. You can define this phase band for both. And by the way, this return map, it is time periodic, but it contains the same evolution information as this time evolution operator. So here are just showing, I'll be using phi and phi tilde to represent the phase band for this U and U tilde. And in some sense, the Floquet band are just a very special phase band, right? So you can just take the small t to be capital T, and then you recover the Floquet bands.
Sorry, Ruixing, just one clarification question. The phase band is different from the quasi-energy you mentioned.
Yeah, it's different. The quasi-energy band is basically the eigenspectrum for this U at capital T. But the phase band actually lives in one higher dimension because we also include the dispersion along the T direction. So for a 2D system, actually the phase band lives in a 3-dimensional parameter space because of the additional T axis. So that's the difference. But you can think that the Floquet band is just a very special snapshot of the phase band, where I take small t to capital T. Okay. All right. So okay. So now let's talk about the Floquet topology. So basically, when we talk about Floquet topology, actually there are 2 different categories. The first one is a very natural generalization to the static band topology. Basically, we are talking about the topological properties of the Floquet Hamiltonian. It is still a property of a Hamiltonian. So in this case, for this topology of the Floquet band, everything we know about static system, for example, the topological indices or the classifications, can be directly applied to analyze the topology of the Floquet bands. And the well-known examples are simply we can use the Floquet engineering to generate topological states, even if the initial state is actually a trivial system. And of course, the pioneer work here is done in Maryland, which is by Victor about like 10 years ago. And but in today's talk, I will focus on the second category where it has an additional word called anomalous. And in this kind of category, the topology here is not for the Floquet bands, but instead for this time evolution unitary, this U of t. So in this case, it often have some like very exotic phenomenon that have no static counterparts. For example, this is an example that introduced by Yang yesterday, that you can actually achieve chiral edge mode even if all the bulk bands are topologically trivial. So this kind of statically impossible phenomena are often known as intrinsically dynamical because it is completely coming from the dynamics, the quantum dynamics of the system. And this is another pioneering work, still about a decade ago, done by these people. I think this phenomenon was first introduced. Okay, so yes.
Sorry to interrupt. I'm Hussein. So just about the references. So sometimes I see that the work of Takashi Oka and Aoki is missed. So that is in some sense the first work that shows that by driving, band structures, you can change their topology. So that is in 2009. They don't use the word Floquet at the time, but historically, this is the first work I think to mention.
I see. I didn't notice that. So it would be great if you can send me the reference such that I can put that in our paper, because this is probably the first one that I realized, but it's not necessarily.
The name of the paper is Photovoltaic Hall Effect in Graphene. So there's no Floquet in that in the title. So sometimes people don't notice this.
I see. Thanks for this. Okay, so maybe I can move on. Let me first introduce what do I mean by this Floquet higher order topology. So here are the defining features that I use to define what do I mean by a Floquet higher topology. And just to show you, so this is actually an example of it. And as you can see, this is actually a calculation on open geometry for some model that we'll introduce in the next slide. And as you can see in this quasi-energy spectrum, so it has two gaps. Okay, the first gap happens at epsilon equals to 0, and the second gap happens at this pi energy. And so although there are two gaps, there is no edge state penetrating this bulk gap, but instead there will be localized modes that are around these two corners at both quasi-energy 0 and pi. So this corner mode feature is exactly what I propose to be higher order topological in this sense. Okay, and for this kind of anomalous AS hotties, we will also require the existence of both crystalline symmetry and chiral symmetry to guarantee the robustness of the corner mode. For this, the requirement of the chiral symmetry is pretty easy to understand because we want to pin these corner modes at those special energies, because otherwise you can locally perturb these corner modes such that they can shift energetically up and down and merge with the bulk bands. And to define this word anomalous, we actually require that the bulk Floquet band must be topologically trivial. So this also implies that this kind of phenomena is statically impossible, because otherwise, if in the static system, if you want to have this kind of corner fit, we need to have some topology environment that is encoded in the bulk band. But here, due to the requirement, this is something that it cannot be achieved statically. And this also implies that this kind of phenomenon cannot be diagnosed by any known topology environment that have been developed to understand this static high order behavior. So this leads to a very important open question here: is how can we systematically characterize and classify these AF hotties? So this will be the question that we are trying to answer in this work. Okay, so so let me first show you how I get this basically how I get this kind of spectrum for how I construct this kind of model. So this is a very simple example. So here we consider a unit cell that contains two sublattices. Let's call them A and B. And we know that if we impose a chiral symmetry, then this 1D chain, it has two topological states, right? So the first one is the trivial state of the Su-Schrieffer-Heeger model that has no end mode at all. But the topological state here is where I do have, this zero energy end mode. But for our purpose, we want to construct a 2D topological state. So this can be achieved by simply, doing a couple chain construction. So basically, we just take these chains and couple them together. And by the way, so this model consists of two parts. Okay, the first part it consists is constructed by all these trivial chains, and it lives in this time interval. And for the second part, it consists of this coupling of this non-trivial chains, and this lives in the remaining time intervals. And when you put these two together and form this two-step drive, then this kind of model is exactly leads to these high order features that you have these pi modes and zero modes localized around the corners. So this is a very simple model for these F-hotties. And I want to emphasize that the model symmetries here that are responsible for protecting this corner mode physics is the chiral symmetry and also the C2 symmetry. Okay, the importance of the C2 symmetry here is like these two corner modes are C2 related. So you cannot, so if you want to attach some 1D topological state on the boundary, you have to attach them symmetrically, such that those modes are still robust with this kind of boundary perturbation.
Okay. Hi, Ruixing. Just one quick question. Do you need translation symmetry? Lattice translation symmetry here?
In this case, no. So okay. I only care about a strong topological state. Yeah, that's a very good question. Okay. All right. So to understand why we have this F-hotties, let me first directly jump to the short answer for this. Okay. So we find that all these anomalous Floquet topological phenomena, whether it's like first order or second or higher order, they must be indicated by the existence of singularities that live in the phase band. Okay. So recall that the phase band is the eigenspectrum of the time evolution unitary. And here is just an example of the phase band. Of the phase band spectrum phi. So this direction is a time direction. Okay, so this singularity simply means some gapless bands that lives at the zone boundary of the Floquet zone, of the zone of the quasi-energy of the energy. Okay, so and this red dot is just an example of this phase band singularity. And to understand why this singularity are important for this topological phenomenon, the short answer is this singularity are exactly a footprint of this topological phase transition that separates this topological state from trivial states. Okay, so this is something that we can never imagine in a static system, but in those dynamical systems, and actually the phase band have a memory that can memorize the topological phase transition that it actually occurred. Okay, so here is how it goes. Let's first start from this kind of topological states that have this phase band singularity. Okay, and then we want to gradually increase the driving frequency of the system. And we know that if the driving frequency goes to infinity, we actually goes to a static limit, right? Because this is where we recovered infinitesimal translation symmetry in time. Okay, and but on the other hand, as we start to increase the driving frequency, we actually start to stretch the phase band, and namely we are pushing this singularity further towards a positive time direction. And this green line here is actually shows the special moment where the small t equals to capital T. So when the phase band intersect with the green line, then the intersection, the spectrum living at the intersection are exactly the Floquet spectrum. So as you can see, as we start to increase the driving frequency, we actually will come to a very special moment where this singularity exactly becomes a band gap closing at pi energy. And this is exactly the topological phase transition that we're talking about, which separates this topological state to a static state. Okay, so this is why this singularity is important for this topological state, and it generically occurs in no matter whether it's a first order or higher order topological state. And another thing that I want to point out is this singularity is a necessary but insufficient condition for achieving this topological phenomenon, because not all of these gap closing will signal interesting boundary features for this kind of topological phenomena. So then the logic here is pretty clear. So we want to classify all possible singularities that can live in the phase band. Okay, that's the first step. But then we will have to figure out what kind of singularity can actually correspond to interesting boundary features. Then we will just quotient out those boring singularities that have no boundary consequence. Then the remaining sector of this singularity is exactly will lead to this a classification of these AF Hotties. Okay.
Sorry.
Yes.
So I'm just curious. Here you plot a phase band in terms of function of t. How about you do the Fourier transform and plot it as a function of frequency? Like conjugate to t. I'm just curious.
I have never thought about that. But the reason we can plot it as a function of t is because the time is in the Floquet system. Time is similar to momentum. Okay, frequency is actually similar to position. So if you want to get a band spectrum, we have to actually plot it along the time instead of doing that Fourier transformation. Okay.
Okay, thank you.
So that's why we only consider the time direction. Okay. All right. So okay, just to move on quickly, let me just mention that for a 2D system, the phase band actually living in a 3-dimensional parameter space, right? So then we can just think about what kind of singularity we can have in 3D, right? So for the parameter space, yes.
Can I? So this phi. So what is its relation with the time evolution operator in the Floquet picture?
Oh, it is the eigenspectrum of the time evolution operator. Basically, you just take the time evolution operator at any time, at any k, you diagonalize it, and then you get a bunch of unitary phase factor as the eigenvalue, right? Then you take the log, and that's how you get the phi.
I see.
Yeah. So this phase band contains all we want, all we need to know about the time evolution. Okay. Okay. So yeah. So in the 3D parameter space, so we can have either point-like singularity, or we can have something that more like a line or a loop, right? So recall that the KT space is actually a T3 torus. Then we can start to ask what kind of loops can we have? We can either have a contractible loops, but for the contractible loop, they can always be contracted into a point. So the point and the contractible loop are kind of equivalent. So we can just consider a point node to represent all, right? But we can also have these non-contractible loops, which can wind around the brane zone, right? But in this case, if you want to have a stable non-contractible loop as a singularity, then we must require translation symmetry, because otherwise you can always fold the brane zone such that the loops will double and gap out each other. So this means these non-contractible loop singularities, they will correspond to something like a weak topological state that require the protection of translation symmetry. This goes back to Jabin's question. So, but in today's talk, I will only focus on the strong topological state. So this means I can only consider this point node like a singularity in this work. Okay, and in 3D, the most natural or the simplest point node is just a wild node. Okay, which carries a multiple charge. And okay, so let's first start from a wild node living here. And then we notice that the chiral symmetry is actually a mirror of time direction. So basically, when you act this chiral symmetry on this return map operator, it actually will just flip the time around the capital T over 2. Okay, and this since the chiral is just a time mirror, this means if you have a multiple charge here, the chiral symmetry will always require the existence of a chiral partner, which is another wild point living at a symmetric position along the time direction, but carrying a negative multiple charge. So this means the wild nodes here are always coming in chiral related pairs. And this is what we call a dynamical wild pair. Okay, and this word this dynamical because this wild pair actually live in the phase band. It's something that we have in the static solids. Okay, so as you can see, generally speaking, this dynamic wild pair is unstable because you can always deform the spectrum such that these wild nodes meet each other and gap out. But if we have additional cosine symmetry, they can actually protect this wild node from gapping out each other, and thus stabilize this DWP. Here is just an example that I want to to demonstrate how these wild nodes can be stabilized. We consider a C2 symmetry, and in particular, we want the C2 symmetry to anti-commute with chiral symmetry. Okay, so along the rotation invariant axis, which is also the time axis, suppose if you have a right mover with C2 equals to -1, and then because of this anti-commutation relation, then the corresponding left mover, which is related by chiral symmetry, must carry C2 equals to +1, right? So similarly, you can actually plot the other movers for these two wild nodes, and you can see that it actually obeys a very interesting feature that the C2 eigenvalue is always locked with its velocity along the time direction. Okay, and in this case, this means all the right movers and all the left mover, they are living in different C2 subsectors. And then even if you squeeze these two wild nodes together at the same point, you can never add a perturbation that couple these two wild nodes without breaking the C2 symmetry. So this is how the Christian symmetry can stabilize this wild node in this case. But on the other hand, this locking effect between symmetry eigenvalue and velocity, this is something quite highly unusual in a static system. And in fact, you can show that this kind of wild nodes with this kind of dispersion relation can only occur on the surface of a four-dimensional topological crystal insulator. It cannot be achieved in any the wild semi methods we know in static solids. Okay, and this is actually pretty easy to understand because we know that for the quantum Singhua insulator, it always shows this kind of similar locking effect between the spins and the velocities, but only on the boundary of the system as a helical edge-space. So this actually indicates, and we found that this is actually a generic feature for all these robust singularities, that all these robust singularities are related to some kind of four-dimensional TCRA surface. Okay, so this is just to demonstrate how how the singularity for this F hotties look like. And yeah, and we also checked the previous C2 model. And as you can see, this is the phase band dispersion along the T direction. And we also plotted with using different colors to label their C2 eigenvalues. As you can see that all the right movers are having C2 equals to -1, but all the left movers are having C2 equals to +1, just exactly same as what we have described. Okay. So I don't think I have time to get to this part, which is how I caution out this unwanted singularities. But I will encourage you to ask me about this part in the discussion session. Okay, let me just skip this slide. Okay, so this is basically the logic flow for my classification. So for this 2D hotties, we found that its phase band always have these 3D Dirac or Weil-like singularities, and which are related to the surface state of a four-dimensional TCI. Okay, and in particular, we checked the robustness of these singularities, and we then achieved a classification for all these singularities for a given group. Okay, but this classification is not the classification, the ultimate classification of the hotties. To go from this step to this step, we need to know which singularities are responsible for the boundary features. So this is related to the slide that I just escaped, which is some technique called dimensional reduction. So by applying this method, we find that we establish a bulk boundary correspondence, which together with the classification, this together leads to this final classification of the F hotties. So here I'm just showing you some result we get. So for the left table is a classification table for the singularities, and for the right hand side we get the classification table for the F hotties, and you can see that they are not equivalent. Okay, for example, the C2 model that I will show you lies in this symmetry class, and we found that it had the V2 topological classification, but if you check its singularity classification, it actually has a Z classification. So this is because we have already modeled out some of these trivial singularities to achieve this final classification. Okay. So just to wrap up, there are some interesting questions that are still open even within our framework. The first question is, of course, we have a systematic way to classify all these F hotties, but it's not clear to us whether this classification is complete. Okay, so it's possible that we might miss something that is beyond the framework or or within our classification procedure. And there is also ongoing work with Dingyu, Zhang, and Shankar, which we hope to generate this idea to a Floquet BDG system that has this anomalous high order topology. Basically means for 2D system, you can have this quantum errata modes at both 0 energy and pi energy. And another question is, how can we generate this idea to 3D, right? Because in that case, we need to think about the surface state of a 5-dimensional TCI, which is completely beyond my current imagination. But this is definitely an interesting question to ask. And also for the experimental realizations, in our paper, we have like two very simple models, which only involves nearest neighbor hoppings. So this model are in principle can be realized in those photonic or acoustic platforms. So that's why we are talking to Mohammed to see whether these models can be realized in their setups. And the final question here is, in our work, we have defined a set of higher order topological indices to characterize the corner modes, which I didn't go through because that's kind of details. But those indices are practically not easy to calculate. So then the question is, can we have a simpler way to diagnose this higher topology? This question has been partially answered by joint work with Jabin on this so-called dynamical symmetry indicators. I think Jabin will talk about this on Friday, and I'm very looking forward to this talk. So I want to say is that I think this field is just the beginning, and there are a lot of things to explore in the future. And I will leave my final slides with this logic flow. And if you're interested in our work, you can just take out your phone and open the camera, and this is a scan code that will directly lead you to our archive appropriate. I think, yeah, that's basically my talk, and thanks a lot for your attention and any questions.
Ruixing, I have a question.
Yes.
This is Yuan. So yes. For the usual like a free Fermion system in 3+1D, it can be complete classified by case theory, just like for example for the tenfold wave. So when you study the singularity in the phase band, so do you have this kind of structure? So how is it different from the usual free Fermion classification? So like the index you got is different from the table for the case theory, the periodic table. So why are they different?
Oh, I see. There are some subtle differences. First of all, I agree that so first of all, the singularities they should be because they are related to the 40 TCI. So you might wonder that if we can achieve a classification, maybe K-theory based for this 40 TCI, maybe then we can go back. Then probably we can achieve all this classification. But there are some very subtle difference. Is because for example, for this 3D singularity, it's a 3-dimensional parameter space, but one direction is a time direction. Okay, and but the chiral symmetry here is actually like a unitary time mirror. Okay, but in principle, for example, if you have multiple mirrors in a space group, those mirrors must for example, for spinless, okay, then those mirrors must commute with each other, right? But in this case, even for a spinless system, the chiral and mirror, the time mirror and the spatial mirror, they can actually intercommute. So this means the symmetry operation here is not just like a conventional space group, but it's somewhat like more like sometimes the symmetry operation act on each other in a projective way. So that's kind of a slight difference. But I think in general, because everything is contained in the time evolution unitary, so the phase band is just a characteristic of the unitary operator. So in principle, I think everything the K-theory should be able to classify all this. But since I'm not too familiar with that language, so personally I don't know how to do that in reality. Yeah.
Thank you.
Ruixing, I have a question.
Yes.
So we are you made a comment somewhere where these things are protected from adiabatic perturbations. What does adiabatic here mean, especially because these phase bands seem like generically are gapless?
Oh, that's an excellent question. Let me go back to some slides. Okay. let me. Yeah, this slide. Yes, this is actually an excellent question. So the adiabacity here, actually, the effect of being adiabatic, its meaning actually is twofold. Okay, first we want to make sure that the gap we are interested at this green line, which is a Floquet gap, does not close. Okay, this is more like the conventional way of dealing with static system, right? So, but on the other hand, we want to make sure that any deformation or any perturbation that we want to include, it is a smooth deformation to the time evolution unitary. It can be something that is abruptly in the Hamiltonian, but in terms of the unitary, it has to be smooth.
So does this mean we're changing the Hamiltonian slowly on the scale of the Floquet period? Well, wait, sorry. Now I'm confused because.
Yeah,
okay.
I can make a comment about this.
Yes.
We are changing you can think of the continuously changing the time evolution unitaries while preserving all the symmetries and quantum energy gaps. That's the definition of the topological equivalence here.
And the what gaps did you say?
And the Floquet gap.
Floquet gap.
Okay, Floquet gap, yes. Okay. So it just had an additional requirement that we want the deformation to the unitary is also continuous.
I see. Okay.
Yeah. So that's a different from static system. Yeah. Okay.
I just have a quick question. Make sure I understand this phase span. You say that the variable t is more like a momentum in the Floquet.
Yes.
You elaborate on that.
I'm sorry. So the variable t is more like you want me to.
Yeah. I'm just curious. Mathematical. That's probably mathematical truth, but I would like to see because I cannot see it from here. So.
Okay, let me see.
T is periodic, just like Ks and Ky. The band structure is periodic with the first Boolean zone, and the T can somehow periodic.
Yeah, I think this is simply because that when we introduce the Floquet Hamiltonian momentum space, we just have this periodicity in T as a parameter.
Oh, you are saying it's a periodic, like the momentum.
It's periodic like the momentum.
Okay,
yeah.
I see. Okay, then it's fine. Okay, thank you.
And also in the Floquet theory, if you remember that in the Floquet theorem, that the Floquet eigenstates, there's a periodic part that is periodic in T. It's just like the block states that is periodic in T.
Yeah. Yes.
Hey, Ruixing, can I make a comment, suggestion? Or question? Yeah, so I don't know, are you aware of this Josephson junction realizations of Weil?
Maybe not, but I'd like to hear more.
So there's this work by, I guess, okay, at least Julia Meyer and Manuel Jose are some of the people. And the story is just, sorry. So the story is just that you can, I mean, in a multi-terminal Josephson junction, you can treat the phase differences as momenta and get like various like Weil kind of like topological structures. And I think there's some experimental progress in that direction. And then there is there's some interesting signatures in terms of quantization, conductance, and so on and so forth. So, I mean, it seems like a worthwhile realization of this idea might be to like look at those same things in finite voltage or under RF. So time dependence in a Josephson junction is extremely natural because you can either just apply an RF, which is periodic, like or just I think even a DC. So I have to think of, I'm not entirely sure, but I think even a DC voltage, well, typically a DC voltage produces periodic modulation in time, and that counts as Josephson frequency, like perturbation of the Josephson frequency.
So basically, the dimension of the Josephson junction system, the parameter, the dimension of the parameter space in the Josephson junction system is just how many Josephson junction we have.
Yeah, how many? Yeah, exactly. How many terminals you hooked up? So you can get a 10-dimensional space if you want. I mean, I don't think
Okay.
There's really no limit there.
I see. Okay, yeah.
Actually, I mean, of course, I think practically speaking, experimentalists will get less enthusiastic as you ask for more junctions. And the other thing is, I mean, Vlad Manucherian in our department, he has been at least playing with some of these multi-terminal Josephson junctions. So yeah, so there's also some experimental interest locally.
I see. Yeah, actually, I didn't know that because when we proposed the experimental realization in this work, we just find the references on these, on those photonics, cold atoms, and acoustics. Yeah, and that's simply because that in those platforms, people have realized this anomalous Floquet topology insulator, the one that Yang introduced yesterday. That but in principle, I think is the idea. If in terms of the model construction, the techniques used are pretty similar. So that's why we have quite confidence that in realizing, for example, this model in those platforms.
Yeah.
But it's definitely a very interesting suggestion that
I mean, the game in this case is a little different because you're not actually making the a physical, like it's not a spatial. It's really in momentum space. You're not actually making the real space system. So in that sense, it's a little bit it's a little bit different and feels like cheating. But on the other hand, I think the phenomena that you can get from this, so it's more like asking how do these phenomena manifest in this system, where So
I see, but then the question is like in those Josephson junctions, how can I choose a open geometry in real space to reveal these corner modes? That could be some tricky stuff.
Yeah, now that's true. But I think there are some ideas. I haven't followed this myself too carefully. So, but yeah, it's just something to look out for. I mean, I think there are some ideas along the lines of that the charge operators are sort of like dual to the momentum operators, like canonically conjugate to momentum operator, the phase differences, the phase momentum uncertainty relation, and then using that, I think there is some manifestation in terms of the charge and so on. So at least for people have at least attempted to discuss this for a while, where I guess you'd be looking for the surface arcs.
I see.
Yeah.
If they can see the surface from your arcs, then this means they can make some terminations in the
well, I don't know that they have seen that yet, but anyway, it's actually. Yeah, but actually, I think what is easier to see is like bulk response properties. Like I think things like the chiral anomaly and so on have some kind of manifestation. So if the bulk system has a response, then it's more likely to see. Anyway, I don't know. Just something to think about or look up just in case.
Okay, thanks a lot.
Sure.
I want to just make sure one thing since at the end. So your framework here, basically your work only discussed the 2+1D case with symmorphic plane group and the Kerr symmetry, right? Is that correct?
Point group. It's not the framework. It's just our classification. I think the framework can be generalized.
The framework can be extended. The classification is done for these. It's symmorphic plane group is the same as the point group.
Yes.
Okay.
Okay, if there's no more questions, let's thank Ruixing again. And I think today we have student introduction.
Yes.